Welcome to the introduction on embracing uncertainty with Bayesian belief networks. Software development is inherently complex. Traditional testing methods often fall short. Enter Bayesian belief networks, or BBNs, a powerful tool for navigating this uncertain landscape. BBNs are graphical models that represent probabilistic relationships between variables. They allow us to reason about uncertainty in a principled way, using Bayesian probability. By combining prior knowledge with observed data, BBNs provide a framework for making informed decisions about software quality. In our second section, Fault Diagnosis, Pinpointing Bugs with Probabilistic Precision, we delve into how fault diagnosis benefits from the probabilistic reasoning offered by BBNs. Traditional debugging methods often rely on deterministic rules and assumptions, which may not always hold true in complex software systems. BBNs embrace uncertainty, allowing developers to reason about the likelihood of different faults based on observed evidence. Consider a scenario where a software application crashes intermittently. A BBN can be constructed to represent potential causes, such as memory leaks, concurrency issues, or external dependencies. Symptoms like error logs, system performance metrics, and user reports can be incorporated as evidence. As developers gather more data, the BBN updates its belief about the probability of each potential cause. This probabilistic approach allows developers to prioritize their debugging efforts, focusing on the most likely culprits first. BBNs also excel in handling situations where multiple faults might coexist. By identifying the most probable combination of faults, developers can address the underlying issues more effectively. Moving on to our third section, Risk Assessment, Quantifying Uncertainty for Informed Decisions. Software development is fraught with risks. From project deadlines to security vulnerabilities, numerous factors can impact the success of a software project. BBNs provide a powerful tool for risk assessment, allowing developers to quantify uncertainty and make informed decisions based on probabilistic insights. By modeling risks as nodes in a BBN, developers can represent the relationships between different risk factors and their potential impact on the project. For instance, a delay in a critical component's delivery might increase the risk of missing the project deadline. Similarly, a security vulnerability in a third-party library could elevate the risk of data breaches. The BBN then calculates the overall risk exposure for the project, taking into account the interdependencies between different risks. This allows developers to identify the most significant risks and prioritize mitigation efforts accordingly. This information is invaluable for making informed decisions about resource allocation, risk mitigation strategies, and project planning. In our final section, Predictive Modeling, Anticipating Defects. Before they appear, we explore how predictive modeling plays a crucial role in software quality assurance by identifying potential defects early in the development lifecycle. BBNs excel in this domain, leveraging historical data and expert knowledge to anticipate future defects and guide preventative measures. By analyzing past project data such as code complexity metrics, developer experience, and defect density, BBNs can learn patterns and relationships that indicate a higher likelihood of defects. These patterns can then be used to predict the probability of defects in new code modules or features. This allows developers to focus their testing and code review efforts on areas identified as high risk, potentially preventing defects from reaching production. BBNs also accommodate expert knowledge, allowing developers to incorporate their insights and experience into the predictive model. This information can be incorporated into the BBN, refining its predictions and improving its accuracy. Section 5. Test Case Prioritization, Optimizing Testing Efforts for Maximum Impact. Testing is an integral part of software development, but it can also be time-consuming and resource-intensive. Bayesian belief networks offer a solution by enabling test case prioritization, ensuring that testing efforts are focused on the most critical areas. By modeling the relationships between test cases, code modules, and potential defects, BBNs can identify the tests that are most likely to uncover faults. Factors such as code coverage, historical defect data, and the criticality of different modules can be incorporated into the model. This risk-based approach to testing ensures that resources are allocated efficiently, maximizing the chances of detecting and resolving critical defects. BBNs also allow for dynamic test case prioritization, adapting to new information and changing priorities. This iterative approach ensures that testing efforts remain focused on the areas of highest risk throughout the development lifecycle. Section 6. Decision Support, Guiding Quality Assurance with Data-Driven Insights. Software quality assurance involves numerous decisions, from resource allocation to release planning. Bayesian belief networks provide valuable decision support by offering data-driven insights and quantifying the uncertainties associated with different choices. Consider the decision of whether to release a software product or invest in further testing. A BBN can be constructed to model the potential outcomes of each option. By assigning probabilities and utilities to different outcomes, the BBN can calculate the expected value of each decision. This allows developers and project managers to make informed decisions that balance the risks and benefits of different options, optimizing for the desired outcomes. The transparency of the BBN model also facilitates communication and collaboration among stakeholders. This fosters a shared understanding of the decision-making process. Section 7. The Power of Prior Knowledge, Integrating Expertise for Enhanced Accuracy. One of the key strengths of Bayesian belief networks, or BBNs, lies in their ability to seamlessly integrate prior knowledge with observed data. In the realm of software quality assurance, this translates to leveraging the expertise of developers, testers, and domain experts to enhance the accuracy and effectiveness of BBN models. Prior knowledge can take various forms, such as expert opinions on the likelihood of certain defects, historical data from previous projects, or insights into the specific challenges of a particular software domain. BBNs provide a structured framework for incorporating this valuable information, refining the model's predictions, and improving its overall performance. This knowledge can be incorporated into the BBN's structure and parameters, influencing the probabilities associated with different events. By incorporating prior knowledge, BBNs become more than just statistical models. They evolve into intelligent systems that combine data-driven insights with human expertise. This integration of knowledge leads to more accurate predictions, more effective decision-making, and ultimately higher quality software. Section 8. Data Efficiency, Making the Most of Limited Information. In an ideal world, software quality assurance would have access to vast amounts of data for training and refining models. However, in reality, data is often scarce, especially in specialized domains or for new projects. BBNs excel in such scenarios due to their inherent data efficiency, making the most of limited information to deliver valuable insights. Unlike some machine learning techniques that require massive data sets, BBNs can function effectively with relatively small amounts of data. This is because BBNs leverage the structure of the model and the relationships between variables to compensate for data sparsity. This data efficiency makes BBNs particularly well-suited for software quality assurance tasks in emerging domains or for new projects where historical data is limited. By combining expert knowledge with even small amounts of data, BBNs can provide valuable insights that guide decision-making and improve software quality. Section 9. Transparency and Explainability, Unveiling the Reasoning Behind Predictions. As artificial intelligence, or AI, plays an increasingly prominent role in software development, the need for transparency and explainability becomes paramount. Developers and stakeholders need to understand how AI models arrive at their predictions to trust their recommendations and make informed decisions. BBNs excel in this regard, offering a level of transparency and explainability that surpasses many other machine learning techniques. The graphical nature of BBNs provides a visual representation of the relationships between variables, making it easier to understand how the model reasons. By tracing the paths through the network, developers can identify the factors that contribute most significantly to a particular prediction. Furthermore, BBNs allow for sensitivity analysis, which reveals how changes in the input variables affect the model's output. This helps identify the most influential factors and understand the model's behavior in different scenarios. This transparency is crucial for fostering trust, ensuring responsible AI adoption, and making informed decisions about software quality. Section 10. Conclusion, BBNs, a paradigm shift in software quality assurance. Bayesian Belief Networks, or BBNs, represent a paradigm shift in software quality assurance. Their ability to handle uncertainty, incorporate prior knowledge, and provide transparent explanations makes them invaluable for addressing the complexities of software development. From fault diagnosis to risk assessment and predictive modeling, BBNs offer a powerful toolkit for improving software quality and reducing risks. By embracing a probabilistic approach, BBNs move beyond deterministic rules and assumptions, providing a more realistic and nuanced view of software systems. They empower developers to make informed decisions based on data-driven insights, even in the face of uncertainty. By embracing the power of Bayesian reasoning, the software industry can move towards a future where quality is not an afterthought, but an integral part of the development process, driven by data, knowledge, and intelligent tools like BBNs.